Today we're going to talk about power, especially power for AC sinusoidal steady state solutions. You're familiar with the concept of power because it comes about from this definition of dW dt. That's the energy per time. So W is the symbol that we use for energy in this class. So energy per time. Now, you also know that we have dW dQ and dQ dt. So we've just rewritten this using the chain rule here. dW dQ, that is voltage, and dQ dt, that is current. So we are familiar with power as P equals IV. And that is true pretty much for all cases. Now you do realize, though, that we have time-varying currents and time-varying voltages now, so we've got to keep that in mind. For the purely resistive networks, though, we could write this as I squared R or V squared over R, like that. But these really only work if we have resistors in the network. And now we've got resistors, and we've got inductive elements as well as capacitive elements, which are together, I guess, called reactive elements. So we've got voltages that look like this: V sub m cosine omega t plus theta sub v. That's some phase angle. And we've got currents that look like this: I sub m cosine omega t plus some theta sub I. And these are not necessarily the same phase angles. In fact, they're almost never the same phase angles. But these are the same frequencies. And those are the frequencies that are for the entire sinusoidal system. Okay? Now, it is convention usually to do something like this. Since these angles here are different, it's usually common to set one of these as 0 and then reference the other relative to that arbitrarily defined 0. Okay? So usually what happens is you put this one at 0 and then you change this angle right here to theta v minus theta I, like that. So then we end up with voltage that looks like this: V sub m cosine omega t plus theta v minus theta I. And then our I is just I sub m cosine omega t, like that. Okay? Now, this theta v minus theta I, we're going to learn that plays a pretty important role as we go through and we develop our understanding of power here. That's called the power factor angle, and we'll talk about power factor a little later on. But I want to say this right up front, right now, that sometimes it's useful to think about what the extreme cases are. Like if we have a case where we have a purely inductive circuit, then we know that the voltage leads the current. Okay? The voltage leads the current. That means that theta v minus theta I is going to be plus 90 degrees. It's plus 90 degrees because the theta v is larger. Subtract off the theta I. This angle difference then is at its maximum value of plus 90 degrees because the voltage is leading the current, like that, for a purely inductive network. Now, you've already seen this mnemonic. This is Eli the Iceman. So if we have a capacitive network, a purely capacitive network, then theta v minus theta I is equal to negative 90 degrees. Okay? And if we have just a purely resistive network, then theta v minus theta I is equal to 0. So both of those are equal to each other. It might be useful, I think, to keep these relationships in mind as we go through this. It might make things make more sense more quickly. All right? But anyway, this is our what are our voltage and our current, how we're going to express them when we start talking about power here. So if I have P equals IV, what this P is, I'm going to try to remember to put a little P like that, so this is going to be that. The reason is because later on we're going to talk about capital P and little p. This little p right here represents the instantaneous power. Okay, it is the power because I and V are going to be these time-varying functions here. This is the power at a specific moment, a specific t value. And of course, this is going to change over time as time does, so the instantaneous power. Later on, we'll talk about average power and things like that. But I want to distinguish little p right up front. So let's take our voltage and current that we have, and let's plug them in so that we can have our instantaneous power and look at what that expression looks like. So I'm just going to take this V and I value here, and I'm going to plug them in down here. So instantaneous power, which is I times V, is equal to I sub m, V sub m, times the cosine of omega t plus theta V minus theta I times the cosine of omega t. All right, so there is our relationship. We just took the current, that's the I sub m cosine omega t, and the V is V sub m cosine omega t plus theta V minus theta I. Put them together and we get something like that. Okay, so that's not very useful to us in that current form because we can't see what we need to see in order to understand power better. So we're going to use a couple of trig identities here. Here's the first trig identity that we're going to use. We're going to use cosine alpha cosine beta is equal to 1/2 cosine alpha minus beta plus 1/2 cosine alpha plus beta, like that. Okay, so we're going to let alpha equal this right here, so this is going to be our alpha, and then our beta is just going to be that right there. Okay, so let's go ahead and make those substitutions in, and when we do that, instantaneous power, I sub m V sub m over 2 times the cosine of theta V minus theta I plus I sub m V sub m over 2 times the cosine of 2 omega t plus theta V minus theta I. There. Okay, this is a little closer to what I want to get it to. We're still not 100% there, but let's pause just for a minute and look at this because you can already get an idea here about what's going on. Look at this first term here, and you notice there's no time variable in there. There's nothing about that that's time varying. However, all of the time varying portion is this part back here. So we've got something that is essentially constant over time. And then we've got something that is time varying. And it's time varying in a sinusoidal fashion. You notice, though, that the what we had previously for our frequency was just omega. But now, since we multiplied these two things together, our frequency has changed. Our frequency is now twice what it was before. Okay? So I'm just pointing these things out so that you can see them as we go along. This though, is kind of interesting. Over time, think about the way a cosine function, regardless of what the frequency is, how it varies over time. If you've got something that looks like this, well, what's the average of that over one complete cycle? So let's say from there to there, that represents one period, so one complete cycle of oscillation there. Well, what does that average to? Well, if this is 0 down here, then it averages that much above and this much below. It's going to average to 0. No matter what, this right-hand side is going to average to 0. But what about this side over here? Well, this side over here is fixed. It's not going to change. Your I sub m and V sub m are not going to change as long as your voltage and your current do not change. They're not going to change. And this phase angle, theta v minus theta I, remember these are the ranges of that from plus or minus 90 degrees, but for any specific network that you're trying to solve a problem for, this theta v minus theta I is fixed as long as you don't induce changing quantities into it. Over time, this is not going to change. Okay, so we've got a time constant portion and we've got a time varying portion. Okay, well, we're going to name some of these things. And we're going to call this thing right here, this constant over time portion, we're going to call that the average power. Now, why do we call it that? Well, I think it's kind of obvious because if you average it over one complete cycle, this portion, the time varying portion, becomes 0. This portion over here is just fixed. It's a constant value. And we're going to call this is where the capital P comes in. That's going to be I sub m, V sub m over 2 times the cosine of theta v minus theta I. You notice, like I said, that theta v minus theta I pops up a lot here. And that's the power factor angle. So this part right here that I just put in parentheses, that's called the power factor. That'll pop up again later on, you'll see. Okay, well, that's the average power, and that's the constant part. So the instantaneous power averaged over one complete cycle is this right here. So that's the average power. Sometimes you'll see this called the real power. Sometimes it's called the average power, average real power, whatever. Okay. By the way, you might say, well, why is it called real? I'll go ahead and tell you. This is also equal to 1/2 times the real part of V times I star, phasors. Okay, so it's the real portion of I times V. That star there indicates the complex conjugate of the phasor, all right? And that's why it's called the real part, because you're taking the real part of that. Okay? That's kind of just a heads up. All right, if we have a purely resistive network, remember theta V minus theta I are equal to each other. If we have a purely reactive load with either an inductor or capacitor, then this theta V minus theta I is somewhere in the range of, if it's purely inductive or reactive, then theta V minus theta I are these values here, plus or minus 90 degrees. But usually a network is going to have resistive elements, inductive elements, capacitive elements. It's never going to be exactly one of these extreme values here. So it's always going to be somewhere between this plus and minus 90 degrees. So we could say the range of theta V minus theta I is going to be somewhere between negative 90 degrees and plus 90 degrees, like that. Okay. Notice this here. If I take cosine theta V minus theta I, that's the same thing as cosine of the opposite, negative theta V minus theta I, which is, we could just write that as cosine of theta I minus theta V if we wanted to, like that. That's because if I take the cosine of an angle and the cosine of the negative of that angle, then those are equal to each other. So the negative there doesn't really change the cosine value. That's just a trig identity there. So this theta V minus theta I is going to be between plus and minus 90, because both of these and these, since theta V minus theta I are within that range, both of these are going to be positive values. Okay. Okay, let's get back to this and let's go ahead and use our second trig identity and see where that takes us. Here's the second trig identity. Cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And for this one, we're going to let alpha equal 2 omega t, and we'll let beta equal theta v minus theta I, and this is it up here. So this is alpha, this is beta. Now I'm only going to rewrite this last half of this. The time varying portion is what I'm going to apply this trig identity for. This first half, we're just going to leave it in its current state, like that. And whenever I do that, and I plug that in, here's what I end up with for the instantaneous power. P equals I sub m v sub m over 2 times cosine theta v minus theta I. That's just a rewriting of this constant portion up here. Plus I sub m v sub m over 2 times the cosine theta v minus theta I times the cosine of 2 omega t. So that's this first portion here. Minus I sub m v sub m over 2 times the sine of theta v minus theta I times the sine of 2 omega t. Okay, now look at this once again. So we've taken this time varying portion and we've applied this trig identity to it, and we changed just the time varying portion to this and that right there. Okay, we'll notice that there's some repeating portions here. Remember that we didn't change that, but now that we've applied the trig identity, it also shows up right here. And we've got something that looks similar, but it's not exactly the same because this is a sine portion here. So I can take that right there, and remember we made our this definition that P is equal to that. Well, that P value shows up here. This is capital P, this is capital P, and let's define this as big Q. Now don't get those mixed up. You better watch your P's and Q's. But so I could rewrite the instantaneous power P as capital P plus capital P cosine 2 omega t minus Q sine of 2 omega t. Okay, let me remind you, capital P was I sub m v sub m over 2 times the cosine theta v minus theta I, and big Q is I sub m v sub m over 2 sine of theta v minus theta I. Okay, this one I've already said, this is the average power. This one is called the reactive power. Now, as you might guess by the names here, this reactive power is going to come about because of the presence of our reactive elements, the inductor and the capacitor being present in here. Okay, while we've got these things defined here, let's talk about the units for these. Units, let's don't do that one. Big P is going to have units that you're familiar with. It's watts, and that is just capital W. Big Q is going to have units. Now we've got to be careful here because every one of these components here has to have the same units in order to be able to add them together and get out the instantaneous power. But we need to distinguish between the average power and the reactive power. So we're going to give this a slightly different unit name, and we're going to call this a volt amp reactive. Now you might say, okay, well, power, let's go back to our original definition of power. Power is just I times V. The unit could be considered volt times amp. So a volt times an amp, that's what we've defined as a watt. All right. So really, this is just a watt by a different name. And it's volt amp reactive because we want to distinguish the average or real power from this, the reactive power. And if you're thinking ahead, maybe you're beginning to see this, the reactive power is going to be it's going to be complex. It's going to be complex because it's got the reactive elements whose, when you convert them into the frequency domain, are complex numbers, okay? So this one is the average power is probably going to be the real part. The reactive power is going to be the imaginary part. And if you're thinking ahead, you're exactly on track here. Okay, so we've got this volt amp reactive. We need to give this another symbol here. This one is often called VAR. Sometimes you'll see it written that way. I have also seen it written that way with a little r, but either one of those is the same thing. Okay. Now, in just a little bit, we're going to talk about putting the real part and the imaginary part together, and we're going to call that the complex power. So we can put those together, and when we do that, this is going to be a phasor, and the phasor we're going to symbolize as S. The unit for the complex power, you remember it's going to be power. It involves watts, and it involves these var elements as well. So it's going to be watt vars. So what we're going to call this is just a volt amp, or VA. Okay. So if you think about the complex power, that's equal to the real part plus J times the imaginary part. Okay. So this is our definition of complex power, and you can see that it includes both components here. It includes the P and the Q components. All right. Okay, let's do a little problem real fast here. We'll do an example out of the textbook. This, let's say that we've got a circuit that looks like this. It's got a resistor, 4 ohms, it's got a capacitor. We'll go ahead and convert this into the frequency domain, save a little bit of time. 2 ohms and 5 angle 30-degree volt source there. Okay, and let's say I want to find the average power that's being supplied by the source here. Okay, well that would be pretty easy if I could figure out what this current is here, and this would be phasor I. If I could figure out what that current is, then I can go back to our definition right here of the average power. I'll draw a box around that because it's kind of buried inside there. This right here is our definition. It's the same here. So our P, I guess I could have just looked right here. Our P is that, and we want to figure out what capital P is, or average power is for this. Specifically for the source. Remember, power has sort of a perspective to it, so we want to find the average power supplied by the source. Okay, and in order to do that, I need to know what I sub m and V sub m are. Well, V sub m I've already got. That's this 5 right here. And now I need to figure out what phasor I is so I can get I sub m. Well, phasor I is just going to be phasor V over the impedance of the circuit. And phasor V, we know that that's 5 angle 30 degrees. Well, what about Z? Well, we've got 2 impedance elements here that are in series with each other, so the impedance is just going to be the sum of those two. 4 plus, well, minus J2. Okay, we want to do this division here, so that's 5 angle 30 degrees. Need to convert this 4 to and that turns out to be 4.472 angle negative 26.57 degrees, like that. Okay, we need to do the division. 5 divided by that is 1.118 angle, top angle minus the bottom angle. So we're going to add those two together, and it's going to be 56.57 degrees amps. Okay, so that's our capital I, that's our phasor I. So this right here is I sub m. And the 5 here is V sub m. Now I'm ready to figure out what the average power that the source is supplying here. And that's going to be big P. That's going to be V sub m, I sub m over 2 times the cosine of theta V minus theta I. All right, well, that's V sub m, 5 times I sub m, 1.118, divided by 2, times the cosine of theta V, which we've called 30 degrees here, minus theta I, and the theta I was this right here, 56, minus 56.57 degrees. That turns out to be, when you do that multiplication, turns out to be 2.5 watts there. So average power supplied by the source, 2.5 watts in this case. Okay. All right, that's just a quick example problem so you can see how to do the calculation. What we've got here, remember, is we've got instantaneous power is equal to average power plus average power cosine 2 omega t minus big Q sine 2 omega t, like that. Well, I've said this before, but it might be useful to look at those extreme cases. Like, what happens if we have a purely resistive circuit? What happens if we have a purely capacitive circuit or a purely inductive circuit? And I think it'll be useful to see what's going on here. Let me show you something, a graph right up front here, though. I'll see if I can set this up and then maybe zoom in on it here. What I have here in this graph is, I'm assuming that theta V for this particular graph is 60 degrees and theta I is 0 degrees. Okay, and it's kind of messy, but if you look at it long enough, I think you can figure out what's going on here. This dotted line, dashed line, is the voltage function. And you can see the voltage function is going through its cycle here. The solid line down here, that's the current function. And you notice they're both centered on 0 here, just like that. Okay. Well, if you'll think theta V is 60 degrees, theta I is 0, so that means the voltage is leading the current. And how to think about that is the voltage started way back here. If you were to trace that on through, it'll start way back here. The current, however, started somewhere right around there. So, actually, the current would have started right there, and that would have started back here. But the point is, the voltage started first. The voltage started before the current. That's why we'll say that the voltage is leading the current. Okay? We could say it the other way around. We could say the current is lagging the voltage. And that terminology, leading and lagging, is how you talk about the power factor. Okay? But here's what we got. Those two things right there, and they're obviously not in phase. Voltage is leading by 60 degrees. But when you multiply those two things together and you put them in these terms right here for instantaneous power, here's what you get. You get this line right here, which I've said is the instantaneous power. And you notice it's not exactly on 0 the way these things are down here. So it doesn't average to 0. In fact, it averages to whatever the center line is here, right in that area right there, which if we were to perform a calculation on it is going to be this right here. Okay, so it's going to be I sub m v sub m over 2 times the cosine of theta v minus theta I, which is 60. So what is the cosine of 60? That's going to be 1/2. So it's going to be 1/4. So it's going to be right around in there. It's going to be 1/4 of v sub m I sub m over 2. Okay, so if you'll look at the scale here, this is 3/4 v sub m I sub m. This is 2/4, so 1/4 is going to be right around here. Okay, so that's the average value right there. Okay, I just wanted to show you that so that you could see that it doesn't average to 0 even if you have voltage and currents that look like this that average to 0 over the course of one cycle. The instantaneous power doesn't necessarily average to 0. In fact, it's not going to average to 0 because of this average power that we've got here. And of course, where it, whether or not it's up here, down here, so forth, depends upon what these theta v minus theta I, in other words, what the power factor angle is. Okay. So once again, we're going to look at these extreme cases. Let's start with a purely resistive network. So purely R circuit. Well, purely R circuit, we've already said this. Theta v minus theta I is going to be 0, so that means theta v is equal to theta I. And what happens with P and Q? Well, let's go back and look at those. P and Q were right here. So theta v minus theta I and theta v minus theta I are equal to each other. So this is going to be 0. What's the cosine of 0? It's going to be 1. So you're going to have a value for P that is I sub m v sub m over 2. So you will have a P value, capital P value. You will have an average power, but you will not have a reactive power. And that makes sense if you'll think about it, because there's no reactive elements. The inductor and the capacitor are the reactive elements. This, for our example that we're talking about, is only a resistive network. So this is going to be 0 because the sign of 0 is 0. So you'll have a capital P. You will have a Q that is 0. So what does that mean? You've got Q equals 0. And then because P is going to have a value, the instantaneous power is just going to be P plus P times the cosine to omega t, like that. So that's the instantaneous power. And it's going to be real. It's going to be a real number. It's going to be a real power. It can never be negative. Okay, it's going to vary over the course of one cycle because of this t value here. Nevertheless, it's never going to be a 0 value as it does that. Okay, because why? Because this cosine term in and of itself is going to have a range between plus and minus 1. Okay, so when it's plus 1, that's as big as it gets, and we're going to have P plus P, so this will be 2P at its maximum. Okay, but when it's negative, when the cosine is negative 1, then we've got P minus P, and we've got 0. So this is going to range between 0 and 2P. Okay, so the instantaneous power is going to have that range right there. That's why it's never going to be 0. You're never going to get a negative instantaneous power out of a purely resistive network like this. So it can never be less than 0, like that. Okay, just going through this. Let's talk about purely capacitive. So purely capacitive network. Now, for the purely capacitive network, remember, ICE is the mnemonic that applies here. You've got capacitive network. The current is ahead of the voltage. So what does that mean? That means that theta I is going to be larger than theta V. Okay, because I starts first and E second. So if I think about what theta v minus theta I could be, the I is going to be larger. This one's going to be larger than that one. So this whole thing's going to be negative. And at its maximum value, since it's purely capacitive, it's going to be negative 90 degrees. Okay, so it's a capacitive network. Okay, well, what does that do to P and Q? Well, what's P going to be? P, look back here again. P is this right here. Okay. What's going to happen to that? At 90 degrees, negative 90 degrees, what's a cosine of negative 90? It's going to be 0. So this capital P is always going to be 0. Now, what about the instantaneous power then? This term goes to 0, that term goes to 0, and we're left with just this. So big P is always going to be 0. Then the instantaneous power is going to be minus Q times the sine of 2 omega t, like that. Okay, that negative sign right there is part of the instantaneous power. But think about what Q is going to be here if we have theta v minus theta I as negative 90. This Q is given by this right here. So if this sine of negative 90, that's going to be negative 1, always negative 1. So Q is always going to be negative. So this is negative and this is negative, which means that this is going to be a positive value. And what happens to this over time, it's going to vary between, well, plus and minus 1. Like any sinusoidal, at maximum it's going to be plus 1, at its minimum it's going to be negative 1. So what's going to happen here? You've got this positive value here, and this is going to be between plus and minus 1. What's going to happen over time, over one complete cycle then, this is going to average to 0. Okay, so instantaneous power for any instant in time, t, if you knew that moment in time, this could have a plus or minus value depending upon what this angle is here. So the instantaneous power could be positive, could be negative at a moment in time, but over the course of a complete cycle, it's always going to average to 0. So notice a couple of things here. It's reactive. In fact, it's reactive only. There is no resistive or real portion to this. It's only reactive. And over the course of one cycle, it averages to 0. Okay? Now, that means that there's going to be no transformation of energy to non-electrical energy. So if you need to turn a motor or you need to dissipate heat or something like that, you need some resistive elements in there in order to do that. It's not going to work for a purely capacitive element. And you'll also see here in just a moment that it's not going to work for a purely inductive as well. Let's do that case now. So the last of our extremes is going to be purely inductive. And for that one, this is the Eli case. We've got the inductive element and the voltage is leading the current. If the voltage is leading the current, then theta V is greater than theta I. That's what this Eli is telling us here. So theta V minus theta I, since the V is going to be larger than the I portion, then this is going to be equal to a positive value. And if we are purely inductive, it's going to be at its maximum of plus 90 here. Okay, what does that do to P and to Q? Let's go back and look here. So this is plus 90 degrees. What's this going to be? That's going to be 1. So the P, this is not going to be 1. The angle here is going to be 90 degrees, and the cosine of 90 is going to be 0. So the P is always going to be 0 there. And that makes the instantaneous power only have the Q component. So it's going to be minus q sine omega t, like that. Okay, once again, this is reactive only. And you know, regardless of what's happening with what the sign is of the P or the Q, doesn't really matter. It's still going to average to 0 over the course of one cycle, so there's no way to transform the energy to do some type of non-electrical work. Well, there may be energy present in the inductor, there may be energy present in the capacitor in our previous example, but that energy is going to be swapped back and forth between the elements here, and it's not going to be able to get out of the circuit in order to do something like, I say out of the circuit, it's not going to be able to do other types of non-electrical work, like I said, turn a motor or do something like that. So in order to get non-electrical work out of this, then what we need to do is we need to have cases where theta v minus theta I is 0. That would be the perfect case. You'll never get to that position. That would be the perfect case. And remember, perfection never really happens. So you want to get as close to that as you possibly can, though, because that means that you'll be able to get the maximum amount of non-electrical work out of the system as you possibly can. Okay, we've called this the power, oh, my writing is terrible, power factor angle. Okay, so that's a power factor angle. Then this cosine theta v minus theta I, that popped up quite a bit. That is what we're going to refer to as the power factor. Okay, so the power factor is always going to have a range between 0 and 1. And that's because whatever this angle is in here, if you take the negative of it, the cosine of the negative of it, it's still going to be 1. So because we are limiting theta v and theta I to plus and minus 90 degrees here, the cosine of that is always going to be between 0 and positive 1 here. Okay, so we'll symbolize that as just PF, power factor. Now, there is that other component here for the instantaneous power, which is this sine of theta v minus theta I for Q. And let's call that something as well. Theta v minus theta I. See, it's still got the power factor angle in there, but it's the sine of it. So this is the reactive factor. So the power factor is really the one that we are probably more interested in to maximize, to try and figure out what maximizes this right here. And this reactive factor, we probably want to lower that as best as possible. Now let's think about the range that it could be, since theta v and theta I are limited to plus and minus 90 degrees, and the sine is going to be between negative 1 to positive 1. So it's going to be somewhere in that range. Whereas a power factor is always going to be in that range, reactive factor there. So let's call this RF. We'll symbolize that as RF, and that's our reactive power. Okay. Now a perfect power factor would be 1. So that's what we want to shoot for. We want to try to get the power factor to be at its maximum value here. It'll never really get there, but you want to get as close as possible. So let's say you've got a power factor that's equal to 0.8. That's actually not a very, very good power factor. But let's say that that's what it is. Then what is theta v minus theta I equal to? Okay. Well, you could figure out, just do the inverse cosine of that right there. You get 36.87 degrees. But remember, cosine of some angle is the same thing as the cosine of negative that angle. So you don't really know, based upon just the power factor itself here, whether or not theta v minus theta I is 36.87 or if it's negative 36.87, because there's no way to tell whether it's positive or negative based upon only that right there. So what you can say is that theta v minus theta I is one of those two things right there. Okay. You have to rely upon this reactive factor if you want to figure out which one it is here. Okay. So that means that if we only have the power factor here, there's some ambiguity in this phase angle difference. So that's the reason that we need that reactive factor in there as well. Okay. All right, some terminology here. We've already used this terminology, but we'll have lagging power factor. Now, what's lagging here? Well, that means that the I lags the V. Okay. Now, if I is lagging, we've talked about that case. That means the I is behind the voltage. So that's the Eli case. That means that we have an inductive circuit. Okay. So if the I is lagging, then we've got an inductive circuit. Okay. How do you fix that? How do you change the power factor with an inductive circuit? Well, you add more capacitive elements into it, and that will help cancel out the inductive part. Now, you don't just willy-nilly throw these things in, but your goal here is to have your power factor to be 1. And if you've got this case here, which is inductive, then you can fix that by adding capacitive elements in. You could also have a leading power factor. Now, power factor, what's leading what? That means that I leads V. Okay? And what case is that? Okay, what I is in front of the voltage, that's the capacitive. So we've got a capacitive network then. Okay, so because this will never be exactly 1, then you're either going to lean one way or the other. You're going to have an inductive or capacitive. Well, that means the power factor oftentimes has this extra terminology attached to it. If you don't know what the reactive factor is, and there's no way to tell, whether your angle is positive or negative, the way we've got in this case right here, then by supplying this terminology, leading or lagging, then you'll know which case it is, whether or not it's theta v minus theta I positive or theta v minus theta I negative. So oftentimes you'll see somebody say there is a power factor of 0.8 lagging. Okay, so you've got a lagging power factor. So this terminology leading and lagging here are going to be useful when it comes to determining if this is positive or if it's negative. Because if it's positive, it's inductive. If it's negative, it's capacitive. Right? I should say that differently. If it is lagging, then it's inductive and the angle is positive. So that would be a positive 36.87 there if it were an inductive circuit. And that would be a negative 36.87 if we had a leading power factor. The leading power factor is capacitive, and that would be negative there. Okay, so that's the way you trace down that. This little extra terminology here, the leading or the lagging, is going to tell us if it's positive or negative, like that. Okay. All right. Now, given all of that, we should be able to put some of the pieces together and work a problem or two. I'm going to show you a table here, and you might want to copy this table down yourself. This little table is something that I created for myself, but it just helps me, I think. This, for an R value, the theta v minus theta I is 0. X sub L and X sub C, remember that's the inductive reactance and the capacitive reactance. And the inductive reactance is always omega L, omega L, omega L. And the capacitive reactance, that was 1 over omega C, 1 over omega C, 1 over omega C. But you notice I put a question mark here in between because for the purely resistive circuit where we've got a theta V minus theta I equal to each other, then these two things are equal to each other. Remember, the omega are the same here. So the L is going to be 1 over C. So omega squared, if we solved this right here for omega squared, I know that says omega 2, but that should be omega squared. There's just no way to write it easily because I did this with Excel. The omega squared is going to be 1 over LC. Okay, omega squared for the inductive is going to be greater than 1 over LC, but for C it's going to be less than 1 over LC. Okay, now this is the plus and minus 90 degrees that we've already talked about for the Eli, the Iceman, which might help you keep those straight right there. And you'll notice that the inductive reactance is greater for the inductive circuit. Now that kind of makes sense. The inductive reactance is what makes it an inductive circuit. So the inductive reactance is going to be greater than the capacitive. But down here it's just the opposite. We're going to have a capacitive reactance that's larger, and the capacitive reactance is what makes it a capacitive circuit, which makes the I supply as opposed to the Eli. Okay, but if you just all that we're doing here is we're taking this relationship and we're solving for omega out of it. And omega squared in each of these cases is either going to equal 1 over LC, it's going to be greater than 1 over LC, it's going to be less than 1 over LC. So that means the omega is the frequency of the source. So if it's operating at above its resonant frequency is going to be 1 over LC, or omega squared equal 1 over LC, so omega is going to be 1 over the square root of LC, then that's operating at resonance. And the power factor is 0, like that. Okay, but if it's above resonance, meaning that the omega is greater than 1 over the square root of LC, then the I is lagging, the current is lagging, so we have a lagging power factor. And Q is going to be greater than 0. If we have a omega that is less than 1 over the square root of LC, so it's going to be operating below its resonant frequency, and the current is going to lead, so we have a leading power factor. Now, I put this together myself just so that I could keep it straight and have this as a reference, a quick, easy reference to it. I made some other notes down here, and hopefully you get this. This is the inductive reactance, the capacitive reactance. These are the reactive elements, and these are the resistive elements, and together all of those make up the impedance. And just some more notes here. If omega L is equal to 1 over omega C, then you solve it and it becomes this. And that's the resonant frequency. And then you compare the frequency of the generator to that resonant frequency and see if it's operating above or below the resonant frequency. And that's where these come from here. Okay. So these are just little notes that I made to myself. I think that that would be useful for you to put together yourself so that you can do that. And you've got plenty of time to look at this. Stop the video so that you can make your own set of notes here. Okay, but we're ready to take that knowledge now, and we are ready to work a problem. So here comes an example problem. This one probably came straight out of the textbook. Let's say that I've got a voltage that I know looks like this, 100 cosine omega t minus 45 degree volts, and then current is 20 cosine omega t minus 105 degrees amps, okay, like that. And these are related to these black boxes here. We'll call that black box A. Here's black box B, and we have terminals connecting these two. Okay. there is some voltage, V, plus minus across the terminals here, across the leads between the two. And let's say we know that the current is going in that direction from A to B. But the current and voltage are given by these values, and you know, because these are sinusoidal values, sometimes they're going to be positive and sometimes they're going to be negative. That does not mean that these polarities change in the problem or that the current direction changes in the problem. It simply means that the voltage may be positive sometimes and negative sometimes based upon this polarity. Current may be positive sometimes and negative other times based upon this direction here. Okay, so what do we want to find? Well, here's what we want to figure out. We want to figure out where the energy is going. Is the energy going from A to B or from B to A? Let's go through all of those steps here. Okay, now remember, we have a perspective here. So just like you've asked yourself this question before, do I use P equal IV or do I use P equal minus IV? Well, it depends upon which one of these two things you pick. If I pick B for my perspective, then I say, well, P equals IV. I need a positive sign there. But if I pick A, you can see the current's leaving the positive terminal here. It's entering the negative terminal. Then I will use P equals minus IV. So which perspective do you want to use determines which of these equations you need. If I pick B, and the reason I'm going to pick B is because it does away with a negative sign and I don't have a chance of losing, dropping a sign and making a mistake somewhere along the way. So I'm going to use P equals IV, therefore I'm looking from the perspective of B. Okay, got that. Now that that has been settled, I'm going to use P equals IV, looking at B. So I'm going to decide, is B absorbing or is B supplying energy? And let's look at the elements. Capital P, that's I sub m V sub m over 2 times the cosine of theta V minus theta I. Okay, let's look up here. Theta V is negative 45. Theta I is negative 105. Which one of those two is larger? Actually, the negative 45 is larger than the negative 105. Things get larger on a number line as you go to the right. So we have this case, theta V greater than theta I, like that. Okay, if theta V is greater than theta I, what does that mean? Well, theta V greater than theta I, that's going to give us theta V greater than theta I. That means that the voltage is leading. If the voltage is leading, the current is lagging. So I is lagging. That's the lagging power factor. And what does that mean? That means it's going to operate above resonance. I is lagging, and we have a inductive network here. Okay, so this is going to be a case for Eli here. And that means that omega L is going to be greater than 1 over omega C. Okay, or X sub L is greater than X sub C, like that. Okay, well, let's go ahead and start plugging in our values here. Now, I just did all of that kind of as a sidebar. You don't need to do that in order to figure out this. So let's see, I sub m is 20, V sub m is 100. Divide that by 2 times the cosine of theta V, and theta V is negative 45 degrees minus negative 105 degrees, like that. Plug these in and you end up with, let's see, that's 1,000 times the cosine of, and that's going to be minus 60 degrees. Okay. So this is cosine of 60 is a half, so this is going to be 500. And now what's the unit? Well, that's capital P, so it's watts. Okay, now you notice it's positive, so capital P is positive. What does that mean? Well, from the perspective of B, it is positive, so B is absorbing. It is not supplying energy. So as far as real power is concerned, the energy is going from A to B for real power. Okay. Well, what about the reactive? Okay. So we need to do Q to figure this out. So that's I sub m V sub m over 2 times the sine theta V minus theta I. And that's going to be 20 times 100 over 2 times the sine of 60 degrees. I guess I could have just jumped to 1000 because it's going to be exactly the same, times the sine of 60 degrees. And the angle is going to be the same. Plug that into your calculator and you end up with Q equals minus 866.03. And what's the unit going to be? Vars. So var. Okay, now that's negative. So what does that mean? That means that as far as the reactive power is concerned, that energy is going, that B is supplying. Okay? And that energy is going, oh, wait a minute. I made a mistake. I'm going to back up here. This is not negative. It's positive. Okay? And that's what's throwing me off here. So I made a mistake. That should have been positive. B is going to be the same as up here. It's going to be absorbing. And that also means that energy is going from A to B for the reactive. Okay, so reactive power is causing energy to flow from A to B as well. By the way, sometimes these vars here, you may hear them talk about magnetizing vars. Okay, it's just another terminology. If you ever hear that, that's what it means. Okay, then that's what the case is for these two angles, for theta V and theta I equal to those two. However, you can see that changing some of this, changing theta V and changing theta I, is going to change whether or not an element is absorbing or whether or not an element is supplying, and the direction of the flow of the energy. And you could have energy, you could have the real power going one direction, but the magnetizing vars going another direction. So let's work an example like that. So let's say we've got kind of the same situation here. We've got black box A and black box B. We'll have V between the two, and we'll still have the current going in the same direction here. And we'll have V, well, let's leave V where it was, cosine omega t minus 45 degrees, and then I will change it, and we won't change anything except the phase angle. Okay, that's volts, that's amps. All right, well, in this case, what's going on here? You see the current is now got the larger phase angle, so the current is leading. If the current is leading, that means I leads V. And if I leads V, then we've got a case that's going to end up with capacitive here. Let's go ahead and get started then. Capital P is still the 1000 times the cosine, now negative 45 degrees minus 15 degrees. And that turns out to be 1000 times the cosine of, okay, now it's negative 60 degrees. What was it previously when we did this? Well, it was positive 60 degrees. So this is not really going to make any difference here because the cosine of negative 60 is the same as the cosine of positive 60. So P is 500 watts, exactly what it was before. So what does that mean? That means the energy is going from A to B, and B is absorbing real power. Okay, well, but it does change Q. Q is going to be 1,000 times the sine of those angles, which is going to be negative 60 degrees. And plug that into my calculator, and I end up with minus 866.03 bars. And this time I'm fairly certain that that is negative. So what does that mean? That means that energy in this case, from the perspective of B, because that's negative, energy is going from B to A. Okay, B to A. So that means in this case, B is supplying magnetizing bars. Okay, so it is supplying reactive power here. Okay, now let's think about power factor. Power factor and reactive factor. For this first case back here, for this case right here with these two phase angles, let's see, power factor was cosine of negative 45 degrees minus negative 105 degrees. So the power factor is this thing right there. And that was, well, that's going to be cosine of 60, so that's going to be a half. So we've got a power factor of 0.5. Now, was the power factor leading or was it lagging? Well, the I is behind, so we would say that's a 0.5 lagging power factor. Okay, so we got a lagging power factor. What about the reactive factor for this one right here? Reactive factor is going to be sine of that, so minus 45 degrees minus negative 105 degrees. And the reactive factor is going to be, well, that turns out to be 0.866. Okay. Now you don't have the leading and lagging attached to the reactive factor. That's because the sign in here is carried through. It doesn't just disappear because like it does up here for the cosine. So that's your reactive factor right there. So 0.5 lagging power factor and 0.866 reactive factor. Okay, but now let's look at case 2, the second one back here. What's the power factor going to be? Power factor is going to be, well, it's cosine of negative. Power factor is going to be exactly the same. The difference is now the current is leading. So we got a power factor of 0.5 leading. Okay. What about the reactive factor though? Reactive factor is going to be this right here, and the reactive factor, that's going to be negative 0.866. Okay. So in these two cases, we had different phase angles, and we got very different answers for the reactive power. The real power stayed the same. So in order for us to distinguish power factors in those kind of cases, is we need to add on this leading part or this lagging part here. And how did I figure out the leading part or the lagging part? I just looked up here and saw which one of these is bigger. And if theta V is greater than theta I, then we've got this situation. It's inductive, so that means lagging. The current is lagging, and it's always from the perspective of the current. The current is lagging. And over here, the 15 is greater than the negative 45, so the current is leading, and that means that we've got leading. I is in front of the voltage, I is in front of the voltage, so we've got capacitive here. Okay, so that's important that you be able to distinguish the leading power factor from the lagging power factor like that. Okay. All right, let's go on. We've already mentioned complex power, what that is. So just to remind you, complex power is going to be like a phasor, and it consists of the two portions, the real power and the reactive power here. So the part that's the real, that's due to the resistors, and the reactive, that's due to the capacitors and the inductors. So if we've got both of them in a circuit, then you're going to have both of these components here, unless it's perfectly balanced, in which case the Q is going to be 0. So big P, that's watts. Big Q, that's vars. And big S, that's volt amps here. Okay, now this is called a complex power, and it's defined that way right there. If you were to think of this as being drawn on the complex plane that we've been using, this is the real axis, this is the imaginary axis, then this is the real portion. Let's say the power itself is at that point right there. Then this portion right here is along the real axis. That's P. That's the big P here. This portion right here is along the imaginary axis, and that's Q. Okay, what does that make this right here? That makes that the S here. And the magnitude of S is just the square root of P squared plus Q squared. Okay, this is called apparent power. That's the apparent power. And then, this angle here, let's call that phi. Tangent of phi is Q over P, like that. And that phi is really theta V minus theta I. There. Okay? So let's suppose that, we've got another example here. Let's say that we've got an electrical load. Okay? It operates at 240 volts RMS. Okay, remember that RMS. The load is going to absorb an average power of 8 kilowatts at a lagging power factor of 0.8. Okay. Question is, what's the complex power? And what's the impedance of this load? So we've got an electrical load. The load is what operates at this voltage here. And the load is absorbing that much energy per second. So it's absorbing, and this is average power. And the average power, remember, we gave that the symbol capital P. So this 8 kilowatts here, that's big P right there. And this is, and it's absorbing it at a lagging power factor of 0.8. Okay, so the power factor is lagging. What does that mean? That means that I is behind E, and we've got an inductive case. So this is going to be an inductive load. Okay, and what does that mean? That means that Q is going to be greater than 0. It's going to be positive. If that confuses you, you can go back and add that to your chart if you want to, about what values Q are going to have. For purely resistive, Q is equal to 0. For inductive, Q is greater than 0. For capacitive, Q is less than 0. Okay. So that means that Q is going to be positive in this case. That also means that theta V is going to be greater than theta I. Okay, well, if that's the case, then we're after S. S is defined as P plus JQ. We know what P is already. That's the 8 kilowatts, so we need Q. Let's go ahead and try to figure out what Q is. Q is going to be I sub m v sub m over 2 times the sine of theta v minus theta I. The question is, what is theta v minus theta I? Well, we should be able to figure that out because power factor is 0.8, and that is the cosine of theta v minus theta I. All right, well, we can figure out then that theta v minus theta I is going to be the inverse cosine of 0.8. And that turns out to be 36.87 degrees. Okay. Now, is that plus or minus here? Well, since theta v is greater than theta I, we figured that out based upon the fact that this is an inductive load, then theta v minus theta I, this is going to be positive because theta v has to be larger than theta I, and we know that the combination is already that. So, there. That's the positive 36.87. That's right. Okay, then let's go ahead and do reactive factor at this point. That's going to be the sine of theta v minus theta I. So that's going to be the sine of 36.87 degrees. And it's important that we include the correct sign here, so that's why it was important to figure out if that's positive or negative back here. And that's going to equal 0.6. Okay. So what was P? Well, we already got P. Now we're ready to do Q. So Q is I sub m v sub m over 2. Problem is, do we have that? Do we have I sub m v sub m? We're not really given that, I guess. We could figure out what v sub m is here. We could go through the process of figuring out what z is and maybe figure out what I sub m is, but there's an easier way. And the easier way involves our understanding of this triangle up here. Okay, remember the triangle, PQS. Okay, well, magnitude of S is going to be P divided by the cosine of theta v minus theta I. Okay. How did that come about? Well, S is this right here. S is phasor that. So if we were just treating this like a triangle, then that's P, that's Q, and this is just the magnitude of S right here. That. So rather than worry about it being a complex number, we'll just call it the magnitude. Then the magnitude of S that's just P over that. And why? Because look at the cosine. Cosine of this right here is just P over magnitude of S. And the sine is, well, that's opposite over hypotenuse, so it's Q over magnitude of S. Okay, so this gives us a way to get P and Q because magnitude S is also going to be Q over sine theta v minus theta I, like that. This is what's going to allow us to get to Q then. Okay, but in order to get to Q, I need magnitude of S times the sine theta v minus theta I. Sine theta v minus theta I already know what that is. That's the 0.6. So how do I get the magnitude of S? Well, you get the magnitude of S from this portion up here. Because you know what P is. That's 8,000 watts divided by cosine theta v minus theta I. And cosine theta v minus theta I, well, that's the power factor. That's just 0.8. So 8,000 divided by 0.8, that's what magnitude of S is right here. And that turns out to be 10,000, 10 kVA. Okay, so we'll take that, plug it in over here, 10 kVA times, let's just say 0.6. And now our Q turns out to be 6 kVAR. There. We got now our complex power. S is going to be P. Where did P go? Oh, that's the 8. Plus J 6. And this is going to be K VA, like that. Okay, so there is at least part of our answer. We've got that portion done. Now, we need to figure out what Z is. So let's try and get to that right now. P, we've been writing it this way. I sub m, V sub m over 2 times the cosine theta v minus theta I. All right? I'm going to show you another way to write that. There is, and we've talked about this before, I RMS is equal to I sub m over square root of 2. Well, when we're talking about power, oftentimes this RMS value is given a different name, and it's called EFF. That means the effective value. So if you take the I sub m and the V sub m, and rather than writing it as 2, write this as square root of 2 cosine theta v minus theta I. Then this and that are the effective values. So this is I effective, V effective, like that. And remember, those are effectively the same thing as the RMS values here. So what does that mean? That means that big P could be I effective, V effective, cosine theta v minus theta I. Now the reason I wanted to show you that is because back here in our problem, we're given this RMS value, and that is V effective. That is the electrical load that operates at that RMS value for voltage. We will call that our V effective. That's just some new terminology that they throw in here for when you're talking about power. So I effective and V effective. Let's see. That has to equal 8,000 watts. That 8,000 is what we were told was part of our problem here. 8,000 kilowatts is what P is. So I know what this is. I know what that is. So I can write I effective times V effective, which was the 240 V RMS. That's the unit. Times the power factor, 0.8, is equal to 8,000 watts, like that. Then I effective is equal to this 8,000, excuse me, 8,000 divided by 240 divided by 0.8. And now I effective is 41.67, and that's going to be amps, but it's amps RMS. Okay, so given that then, remember this equation, V equals IZ, then Z is just going to be phasor V over phasor I. So phasor V is, well, I sub m, I'm sorry, V sub m over I sub m. But look here, if I write that over square root of 2 and put that over square root of 2, then this is V effective and this is I effective, like that. So I know what each of these are here. V effective, that was the 240, and I effective, I just can't figure that out right there. So Z is going to be 240 volts RMS over I, which is 41.67 amps RMS, and that turns out to be 5.76 ohms for Z. And that's what Z is. There. We just figured it out. Now, question is, that's the magnitude of Z. So what could this be written as? It could be written in alternative form as 5.76 angle 36.87 degrees. Where did that come from? That, we figured out, is what our theta V minus theta I is. There. If you were asked to write it in rectangular form, I've done that as well. 4.6 plus J 3.5 ohms, like that. So there's our Z. That's our final answer for Z. Here's our final answer for complex power. So we've done what we set out to do. We figured out what S was. We figured out what Z was. I would learn how to do this if I were you. You're almost certainly going to be asked to do something like that on an exam that I sense is in your future. Probably on your final exam. Okay, well, let's turn our attention to that complex power, because you're used to seeing power in different forms. We've already said you know that P equals IV, but you also know that P equals I squared R. You also know that P equals V squared over R. So it just holds to reason then that this S, which we have written this way, that this S can also be written in different forms, and it can. First of all, you can plug in for P and you can plug in for Q. And when you do that, you're going to get the usual forms that we've seen. That look like that. And if I were to, I could change this up a little bit, factor out the V sub m, I sub m over 2, and now what have I got? I've got cosine theta V minus theta I plus J sine theta V minus theta I. That is the Euler identity. You have seen that. That's really the basis for our for writing phasors in the first place. So we could write this as V sub m, I sub m over 2 times the Euler identity. But now let's express that as a phasor, and that's just, I mean, this whole thing, you can think of it as a phasor. This is the amplitude. And remember what a phasor is. A phasor is a quantity that has amplitude and phase angle information. Well, these are the phase angles here. So that's V sub m, I sub m, angle theta V minus theta I, like that. So that's another way to write this whole thing out. And the complex power. And we could, and I've already shown you, you could take the V sub m square root of 2, I sub m square root of 2, and since that's the Euler identity, you could write that as e to the j theta V minus theta I, like that. And then you could separate out that's V effective, that's I effective, and now you can separate that as e to the j theta V times e to the minus j theta I, like that. And you could separate this as V effective, e to the j theta V, and I effective times e to the minus j theta I. So I put the the voltage and its phase angle together, the current and its phase angle together. And now I can write this as, well, this is just, remember this is a phasor, so that's V effective times its phase angle multiplied by I effective times, and this is minus that, so that's minus theta I. Okay, that minus theta I right there, that changed the phase angle of it, so that negative sign was kind of important to carry along, but it changes the angle here. So I could write this as, well, this is V effective phasor, and this is I effective phasor, but with a different phase angle, so that means star. The star is a complex conjugate. Hopefully you remember this. If I've got R plus JX as my complex number, then R minus JX, that's the complex conjugate. So if I call this one A, then this one is A star, and it's just the complex conjugate. So by changing the phase angle like that, we've effectively made the complex conjugate here. Okay, well, there's another way to write the complex power there. And these are phasors, so everything in here is a phasor. We could also, write it, what was it, this way? There's lots of different ways to express the complex power. I want to show you one other. I'm not going to go through the derivation of this one, but S is also equal to 1/2 V, that's phasor V, times phasor I star. So there's another one right there. Now, none of these expressions here have Z in it. If you want to start putting Z into these expressions, then V equals IZ, phasor V, that. Remember, Z is technically not a phasor, so we don't put the little arrow over it. But you could also say, well, that's V equals IZ, then V effective, phasor V effective is equal to I effective times Z. So that works as well. And then if that's the case, then you can make your way back to that one. You could also make your way to other things like, yeah, we've got room here. There's so many of these. I'll just start writing them down. The magnitude of I effective squared R plus J times the magnitude I effective squared X, where X is the reactance. So that reactance is X sub L minus X sub C. There. X is going to be greater than 0 for an inductive network, and it's going to be negative if it's a capacitive network, because the X sub C is going to be larger. So something is an inductive, mostly inductive network if this one is larger, or a mostly capacitive network if that is larger. Another form that you could write that is you can have the I effective squared. Now that just means magnitude. Remember, magnitude of it squared times R plus J I effective squared X. I guess that's what I just wrote down. Okay. So this is like I squared R. That. But now we've got this component over here, which involves I squared, but now it's got the reactive stuff in it there. So it's, yeah, kind of the same thing. That also leads you to, since this looks very similar to what we had previously, this is P plus JQ. So what does that mean? That means P could be written as I effective, magnitude of I effective squared R, and Q could be written as I effective squared x, like that. So lots of different ways to express this. There's another one, S equals magnitude of V effective squared over Z star. And that looks an awful lot like V squared over R, doesn't it, for power? So very similar. Derivations of these can be shown. I'm not going to show any of them, but it's in the textbook. Read the textbook if you want to see the derivations of these. The point is that S comes in a number of different forms. Let's do another problem or two, and then I think we'll be done with complex power and power period, and we can move on and to the last topic for our semester, and that is filters. Okay, so the way that a power company sets itself up is, here's the generators back over here, and these are, you know, at the power plant creating energy, but then they need to transmit it to you or to a company or to an industry or something, and they do that through a line. So this is back over here, this is the source, this is the line, but then you also have the load, and the load could be capacitive, inductive, or something like that. Okay, so the goal here is to have a power factor of 1, remember? But you'll never get there. So if I have a source here that sends throughout the line and to a load over here, the load could be a company or something like that. What I want to do is, you know, before you can fix any sort of power factor, you've got to be able to calculate what current values are. So let's go ahead and do that. We'll give ourselves some numbers to make this easier. 1 ohm, J, 4 ohm, I'm already converting into the frequency domain. That's 39, and this is J, 26. This is going to be a 250 angle, 0 degrees, volts RMS. Okay, let's calculate a number of things. First thing is, let's figure out what the load, current, and voltage are. So let's say that we've got a current going through there, that's our I sub L, and we've got some V sub L plus minus. These are phasors. And let's calculate that. After we do that, we can calculate average reactive power that's delivered to the loads, delivered to the line, supplied by the source, and things like that. So there's only one current here, so the same current, this, even though I've given it a subscript L, it's the same current across everything. So I sub L is going to be the V total over the Z total. So the current depends upon everything, not just the load. V total, that's 250 angle 0 over the Z total, and the Z total, since everything's in series here, we'll just add them all together. That's going to be a 1 plus J4 plus 39 plus J26. So we'll add all those together, 250 angle 0 degrees over 40 plus J30. Okay, this is going to be 250 angle 0 degrees divided by 3, 4, 5. That's a 3, 4, 5 triangle. And the angle is going to be 36 point, what is it? 36. 36.87 degrees. Okay, so I sub L, when we do that computation there, is going to be 5 angle negative 36.87 degrees, and that's going to be amps RMS. and that is what phasor, what we've called I sub L here. If I needed to write that in, let's say, rectangular, then that's going to be 4 minus J 3 amps RMS. Okay, so we've got our current here through our load, which is also the current through everything else here. Then how about the voltage? Voltage for the load, that's just I for the load times Z for the load. So that's going to be 5 angle negative 36.87 degrees times Z for the load. Z for the load is just this part over here, 39 plus J 26. And I need to convert the 39 plus J 26 in order to do the multiplication. And that turns out to be 46.87 angle 33.69 degrees, like that. Okay, now we're ready to do that multiplication, and then V sub L turns out to be 234.35 angle negative 3.18 degrees VRMS, or 234 minus J 13 VRMS. Okay, so there's the voltage of our line up here. This current, I'm sorry, I said line, I meant load. Current of our load, voltage of our load. Okay, then from that we can calculate complex power so that we can get average and reactive power that's going to be delivered to the load. So let's say I go for complex power using this form. Just kind of like P equals IV, so V sub L, I sub L star. You can write down these equations and refer to them, or you can derive them from scratch if you want to. V sub L, that is this. I made a mistake. That should be 234. That's a 3. 234 minus J 13 times 4 plus J 3. That turns out to be 975 plus J 650 VA. I did not do that in my head. I happen to have that written down. So average power, that's big P, is 975 watts, and reactive power, that's big Q, is 650, and what's the unit? Var. VAR, var. Okay, so we've got our S figured out now. That's this right here. From that, we very easily got P and Q. Okay, let's say that I've got another load. Let's make it another 250 angle 0 degrees, and that's VRMS. So there's our load. Our line, let's make it small resistance, small inductance. And then we'll have couple of loads here. Let's say this is load 1, and over here load 2. Okay, This is going to create some currents. Let's say we'll call that one I1, that one I2. And for load 1, we're going to say that it absorbs average power of 8,000 watts at a leading power factor of 0.8. And load 2 absorbs 20 kVA of complex power at a lagging power factor of 0.6. Okay, and what we want to do is let's figure out. Well, there's several things we need to figure out. Let's figure out what the complex powers are for S1 and S2 for the load, and then let's we'll see where if we can go anywhere from there. Maybe we'll just stop there. I don't know. Okay, but anyway, once again, we've got source over here, we've got the line here, and then over here we've got our loads. And let's start by figuring out what S1 and S2 are. S1, you know that's going to be P1 plus J Q1. And P1, we are told what that is. That is 8,000 watts, and that is given to us. Okay, we can find Q1 from this because we're told what that we have a leading power factor of 0.8. So leading power factor means what? Means that the current is in front of the voltage. So it's going to be capacitive network. And leading power factor, cosine theta V minus theta I. What does that mean? That means that theta I is going to be larger than that. So theta I is going to be, so this is going to be negative. So we end up with 0.8, but because of this, we can figure out that theta V minus theta I is going to be the inverse cosine of 0.8, but it's going to be negative. And why? Because the theta I has to be larger. Okay? And when you do that, you can figure out that theta V minus theta I is going to be negative 36.87 degrees, like that. Okay. Now from our geometry, from our triangle here, this is going to be P, and this is going to be Q, and this is now our theta V minus theta I, and it is negative 36.87, so that's why I drew it down like this. So this side is 8,000 watts, and this angle here is negative 36.87, so I could say the tangent of theta V minus theta I is opposite over hypotenuse, so that's going to be Q1, and these are subscripts, 1 over P1, which is going to be Q over 8,000. So tangent of negative 36.87 degrees times 8,000, that's what our Q1 is. And if we do that, we get Q1 equals negative 6,000 bar. Okay. From that, we've got our S1 right now. It's going to be our P1 and our Q1. So it's going to be 8,000 minus J 6,000 volt amps. So there's our S1. We can do the same sort of thing for S2. S2 is going to be P2 plus JQ2. And I know that S2 is 20 kilo VA. That's part of our thing here. We also know that there's a lagging power factor of 0.6. So the lagging power factor is 0.6. The lagging implies that the current is behind the voltage, so this is going to be inductive in nature. And what does that mean? That means that theta V is going to be greater than theta I, or theta V minus theta I is going to be greater than 0, so it's going to end up with positive value. Okay, well, cosine theta V minus theta I is 0.6, so we've got a lagging power factor of 0.6, 0.6, so theta V minus theta I is the inverse cosine of 0.6, and that turns out to be 53.13 degrees for theta V and theta I, and we know that it's going to be positive because of that. Okay, then geometrically, once again, this is our theta V minus theta I. This is magnitude of S2. This is going to be P2, and this is going to be Q2. There. So we should be able to figure out P and Q from that, because the cosine of 53.13 degrees is going to be P over 20,000, and then the sine of 53.13 degrees is going to be Q over 20,000. So this implies, solve that, you get P equals 12,000 watts, and you get Q equals 16,000 VAR. So S2 is equal to 12,000 plus J, 16,000 VA. Okay. Then S for the load is equal to S1 plus S2. That is V sub S times I sub S star, by the way. So this is S for the load. Total is going to be 8,000 minus J, 6,000 plus 12,000 plus J, 16,000. So that's 20,000 plus J, 10,000 VA. So there's S for the load. We just added the two complex powers together like that. You don't do anything fancy because these are in parallel. You just take whatever it is here and now whatever it is there, and you add them together. Okay, because it's power. It's not anything like trying to find equivalent impedances. Okay, so there we've got our two for that. Now we could go on. We could find what's the power factor for the load. Okay, you could find lots of other things, but this video has gone on for far too long, so I think I'm going to stop there. I probably on an exam won't give you anything much harder than the things that we've done here. So let's stop the video right here. Next time we'll start talking about filters.